context need to be properly encoded into some vector. And not only context, we also have seen that not only context, but the words also have to be properly encoded into some vectors. So we have seen that word to vec type of encoding, which is a simple type of encoding. And then you can also have another type of encoding, which is encoding, that is glove. So these are pre-trained networks. They are publicly available. If you have a corpus over which you wanted to do any type of NLP related task, the first thing is that given any word, you need to come up with a encoding for that word. And how you can get that encoding is that you take that, give it to the word to vec encoder or any other encoder, and you are going to get that encoding. So context needs to be somehow encoded into some vector, and inputs also have to be. And inputs need to be encoded in such a way so that we all have understood that it could need to be, inputs have to be encoded in such a way so that related words are having a small encoding, and not related words, they should be having big encodings. And then we have understood that there is going to be a long-term short-term dependency. And if you wanted to have if you wanted to have encoder being trained properly, or decoder, then you need to somehow exploit the temporal dependence which is there between these words within a sentence. So recurrent neural network is coming into the picture. So the neural network, recurrent network, takes the first input and some pre-initialized hidden state and convert it into another hidden state. And using that hidden state, it will generate an output for you. And then if you use such a type of such a type of network for encoder and decoder, then you understand that first the first sequence will go in the, or the first word will go into the encoder, and you will get your hidden state being modified, and then the second word will go and the hidden state got modified, and the third word will go and the hidden state got modified, and finally you will get the final hidden encoding. And that encoding actually being used as the context and being given to the decoder. And decoder need to generate, decoder it's also having its own hidden state along with the previous encoders hidden state. Both of these things got combined, and decoder is going to generate the required sequence word by word. And this is the unrolled version of RNN, in which you all can understand that it's being used to show that how encoding is converting and traveling. Now let us pay another thing, I mean pay attention to certain things. So previous case, when there was not an attention decoder, here you can see that here is the attention decoder which is being shown. Previously it was normal decoder. If it is an attention decoder, not only it will take a final hidden state, it will take all the hidden states, and while generating the first word, it will try to give certain amount of weightage to the first hidden state, second and third, and by which it's going to generate I. And then when it's going to generate M, we all can understand that hidden state 2 can be given more weightage than the remaining hidden 1 and hidden 3. So along with this is actually the attention decoder, that along with its normal functioning of RNN, it is also trying to learn an attention, which you need to say that how much amount of weight that one should be giving to one should be interested to give to hidden state 1, 2, or 3 while generating any output at any instance of time. So it's also going to learn that thing, and that is the thing that we are going to see over here, that the attention at any step 4, which essentially is the step 1, when attention 1 have seen the first input, that is actually the end token, and attention decoder is also having the previous state which is coming from the encoder as well as its own initialized hidden state. Using both of this, it need to be somehow generating the I. How it's going to generate, let us see. The preparing the inputs, what are the inputs to the decoder? H1, H2, and H3. All of these three are the three encoder hidden states. And then you designed a network which is learning these scores, which are being given as 13, 9, and 9, and over that you all understand that we need to apply a softmax, because these weights are going to be used as the they are going to be used as a weighted averaging. So in the fourth step, it's being shown that certain hidden states may get higher weights and certain hidden states may get lower weights, which means that when these weights are being multiplied, you can see that H1 is going to be multiplied by 0.9 and H2 is going to be multiplied by 0.2 and so on. And when you add, you are going to get a context vector, and this is the context. Previously the context vector was fixed for all the time steps. Now the context vector is being changing because your inputs remains to be the same, but these attention or the weights which are given to different H1, H2 and H3, they are continuously changing depending upon the time step or the output that you are generating currently. Similarly, the hidden state of the RNN, the decoder RNN, is also changing. So this blue thing and the purple thing, they are going to be concatenated, and using both of them as the hidden state and the current, the end thing, it's started to generate things for you. Attention decoder. So how it's being done, you can see over here as well that encoding state is actually being given in completely total left of that. You have and it's giving input as H1, H2, H3, which is being fixed because the work of encoder is actually done, and RNNs are sequential. Encoding is actually being done, and after that only decoding is going to happen. So when decoding is going to happen, your attention decoder is going to get the first token as the end token, and some H initialization is happening, some initialization of the hidden state, and using both of this, attention decoder has got H4. Then at some point of time it will get H5, H6, H7 and H whatever the hidden states, the same way RNN used to get its hidden states. And this purple thing is going to be augmented, or we can say it's going to be concatenated with the context. And how you are going to get the context for t equal to say 4 is that you have got an attention 4. This attention 4 is nothing but weights need to be learned, which are being shown in pink color. Certain hidden states will get high weights, others may get low weight. And when you weight all these H1, H2, H3 using this pink color things, you will get this blue color vector. That is actually the context. There's a hidden context vector. That's actually the weighted averaging of H1, H2, H3, all the previous states, hidden states. And then you combine both of them and send it to your fully connected network so as to get the output for that. Now you can, interesting thing that you can see is that attention 4 is different from attention 5. H1, H2, H3, they are fixed, but the attention is continuously changing. And the reason is that attention need to be given even the input remains to be the same, attention need to be changed depending upon what is the current word that needed to be generated. Yes. So yes. So in this way, in the next slide, it's been shown that in green color, French words are written, and in yellow color, in purple color, English words are written, and the things which are high, they are showing that for I, when you are generating I, that is time step maybe 4. The first French word has given more weightage. Then in the second row, you can see that the second word is being actually given more weightage when you're talking when you need to generate M. And maybe third, because student, if there is only one student, and then probably A has to be there. So A is when you are talking about A, then student is also given certain amount of weightage, and some the second word is also have got some weightage. And at last, when you are generating student, the last word has actually given more weightage. And in this way, they have shown that French and English words, so all of them are actually having a blocking type of amount of weight that's being given. And you all can understand that if there is a one-to-one correspondence, which in the case of sequence most of the time is not being there, if there is one-to-one, then only diagonals are going to have. But usually if it's not diagonal, then even though it's going to be a blocking, because not too far things are going to play a very significant role when you are going to talk about certain predicting some new word. The things which are very close, they are going to play more important role. Yes, so any question till now, then you can ask, then we will go to transformers with this.
What is attention?
Yes, your voice is breaking. Can you speak again?
So what is attention? Attention is
Attention. Yeah. So attention is the weight that you have got. Attention is that you have got, in your copy, you have 5 pages, and and you have actually 5 copies. First copy is for the computer deep learning, and second copy is for English, and third for copy is for Hindi classes. And then what happened that when you are going to come into my class, you have all these copies, but you give more weight to the English copy, deep learning copy. So same thing is actually happening over here, that in this attention, you only learn these 3 values shown in pink color, that how much amount of weight should I have to give to H1 or H2 and H3 when I am going to generate the first output. That is the attention, and attention is keep on changing. Is this okay? Okay, anyone else who want to ask anything?
Sir,
Yes.
sir, in word embedding, how we convert the word into the vector?
How we can convert word into the vector is a very good. Who is asking? Can I know the name? Please tell me your name.
Vaibhav.
Vaibhav, are you? I assume that you have not attended my previous lecture. Yes or no?
Yes, sir.
Yeah, so that is the problem. In fact, what happened is that you have not even attended my previous lecture. Secondly, not even you have viewed my second previous lecture. Now, this is actually not correct, because I have spent probably more than half an hour or so to explain word to vec embedding. So I request that please go and check the online. I assume that it's right now even not being uploaded. That is also true. That lecture is not uploaded probably. I'm not
Yes,
sure.
sir.
So today I will ask Daksh to upload that, and in that we have given that the fair amount of idea that how word to vec is actually working. It's a slightly involved way in which a neural network is being trained, and it depends upon the it uses the concept of n-grams and I am a video. Yeah, so please mute. Yeah, so it will take n-grams, and depending upon the n-grams, you understand that what are the things which are related, and you train a network which will take an input and need to generate its corresponding related vectors, and the distance between them need to be minimized. That is the goal of that word to vec type of network. Once it is trained, you are going to get your outputs like that. That is the thing that's being working in that way. Any other question?
Sir,
Yes.
sir, so what is the ground truth for an attention model? Like, how can you train an attention network? So
Yeah, that's a very
you give ground truth that I belong to J, or something like that, or what is that?
But it's perfectly correct what you have asked, and this is the trick that one should also have to understand given such a network. Let me explain this trick, and this is not happening only here, but in several places this is happening, and it can actually be seen as a type of regularization which is also happening. Let us understand that how these attention networks are being trained, or any in between networks for which we do not have ground truth. So attention is actually nothing but you are trying to learn certain amount of weights. You need to learn these weights in order to somehow get C4 or C5, which when concatenated with the H4 or the uh, corresponding latent variable, should have to produce me the output. So they are being trained end to end. Uh, there is no in between loss which is being imposed over this attention, other than that whatever the attention you are learning, you learn it in such a way so that to facilitate my network to predict I at t equal to 4 and m at t equal to 5 and so on. So they are being trained as end to end.
Sir, so right, if I give an example, suppose I have an sentence, say I am student,
Yeah,
and I want to convert it to French, so that is just we étudiant, and then
yeah,
say I have other training example, say I am a boy,
yeah,
for that equivalent French is something, je suis garçon. So
yeah.
is this thing letting the attention know that I belongs to J or something like that?
Yes. So RNN is going to work for this. Attention is just only going to say that learn certain things which are relevant. So RNN is going to give you the relevant H1, H2, and H3. That is being encoded inside that.
So it is the training examples out of which the attention knows which mapping is towards.
Yes. Yeah. So anyways, the attention, see, let me, yeah. So point is that attention need to understand this thing, and RNN needs to, or the encoder RNN needs to generate such H1, H2, H3, provide it to the decoder so that it can properly generate the output. So attention just have to understand how to pick the most relevant so as to get, the best possible output.
So can we say attention to be analogous to a filter in an image for an CNN type of an image?
Yes, so it's actually you can say that it's learning because you can see that H1, H2, H3 as a feature in which H1 is the first channel, H2 is the second channel, and H3 is the third channel. And attention is nothing but a one by one filter. So it's actually 1 by 1 by 3.
Right.
So it's learning this. So anyways, that is the thing. So that is the probably these attentions are being learned in that way using 1 by 1 filtering.
Okay, sir.
Yeah, is this okay to everyone? Any other question? Once we are crystal clear about the sequence to sequence translation, I'm sure that several places it's being done, and huge amount of work is actually being done using such a type of sequence to sequence modeling, and transformers are being developed maybe in 3-4 years, 5 years back. Before that, NLP and several other things where we were actually working. You can see that RNNs were actually being used, and even if you are using RNNs, you are going to get good performance. And I can tell you the transformers are also going to be very useful for sequence to sequence, and the performance remains to be almost very similar or even sometimes better than the RNN, but they are highly efficient because RNNs are sequential, and they you cannot parallelize an RNN, but transformers are heavily parallelized. So if you wanted to train something and its RNN model is going to take or LSTM model is going to take 7 days, then probably the transformer corresponding transformer model with a similar type of performance or even better performance, it can be trained in say a day or so. So they are very, very fast, and the fast means that they are efficient. So they are not inherently sequential, they are parallelizable. So that is the thing with which we are going towards. So we all understand attention. This is also being said as the self attention because it is learning from its own. It's actually learning that how much amount of attention that one should be giving to its own internal representation so as to get the best possible outputs. So that is the point we are going to see in the transformer. Yeah, so that is actually the self attention. So this is transformer networks, and we are again going to use this Peter Bloem's blog. Right now I have written. So anyways, the same things are actually being written in this site. You can go and read in detail from this URL. We are going to start this self attention again. This is sequence to sequence operation. Suppose that my self attention network is this. I wanted to network or whatever. I want a way by which I can learn or understand what is a self attention, which means that x1s I am going to give. So I wanted to go, and it can also be seen as a sequence to sequence modeling that we are going to do. So I wanted to go, and this is x1, x2, x3, and x4, and I wanted to generate my jana chahta hu. Then you can say y1, y2, y3, and y4. So x I go in, and so y I go out. I have slightly written in a simple way, but it's not that x I go and y I come, because there is not a one-to-one relationship. X1, x2, x3, x4, and xt, t words will go in, and y1, y2, y3, y4, and YTT words are going to come out. So one thing that I actually have missed, and that is, somehow need to be clearly stated. I need to figure out that this self-attention is just a part of sequence to sequence modeling. So right now, I am, if I want to say that I am having a small network that is sequence to sequence modeling, that will take all of these things going in and all of these things going out. In between, we want to know that there is another network. This is self-attention network that will take, x1, x2, x3, and x4, and it will generate y1, y2, y3, and y4 for me. So self-attention is going to be used in between this thing, sequence to sequence modeling. So transformers are actually being used for sequence to sequence modeling. RNNs can also be used for the sequence to sequence modeling. Right now, we all understand that xi's will go in, yi's are going out, and these xi's are going to be x1 or x2 or whatever. They are going to be k dimensional. What does it mean? That if I write capital X, that is my whole input. Capital X is going to be my full input, and this is my x1, this is my x2, this is my x3. So this is my x1, x2, x3, and xt. And because of the fact that they are k dimensional, then x1, 1, 1, 2, 1, 3, 1, 4, and 1k. Similarly, x2, 1, 2, 2, 2, 3, and 2k, and I'm having a t row and k columns. I'm having t rows because my t inputs are there. How many columns? Column number 1, 2, 3, and 4. K columns. Why there are k columns? Because each of my input vector is actually of size k dimensions. Then the self-attention. What's the meaning of self-attention is, and this is the very simple thing, that we wanted to learn wait for this, wait for this, wait for this, wait for this, wait for this. So for all of them, how much amount of weight I should be giving if I wanted to generate the ith output. If I wanted to generate an ith output, I am going to give weights to whom? To this row, to this row, to this row, and to all these t rows. So I am going to get a t dimensional vector. That is actually the w1, w2, w3, and so on, t dimensional vector. And how much amount of weight I wanted to give to this vector, or this, or this, or this. So here you can see that it is just saying that each of these xj's, which are 1 to t, all of my inputs, they are going to get a weight. And how many weights are going to be there? Because I is fixed. So for a given I, for a given output, for a given output, that is ji, I am going to get j such weights, and j is actually from 1 to t. So basically t things. So how you are going to generate one y, if you want to generate y2, then y2 is not only coming from x2. Y2 is going to say that I multiply certain weight to this, to this, to this, to this, and probably this is going to get more weight than this guy, or than this guy, and this guy is going to get minimum weight. Probably they may get slightly better weights than the last one when you are generating y2. But not only one single thing is going to give or generate y2. All I'm learning is actually attention. Attention is going to be, this is actually the self-attention, and this is actually the weight that I somehow try to find out or learn or come up with, which will say that I wanted to somehow find out that if I wanted to generate y2, how many or what are the things which are related to this y2. So obviously this thing is going to have more relationship. Probably these things are also going to have more and more relationships. So those things which are having more relationships to generate y2, they are going to get more and more weight. So now you can see that if I wanted to generate any yi, this is actually the vector for this yi, k dimensional vector. Then what you are going to get is that x1, x2, and what are these x1? X1 is this, x1 is this, x2 is this, x3 is this, and xt is this. So these are, what are they? The full row. This is actually the full rows. So this full row, I'm going to get x1 multiplied by a weight, x2 multiplied by a weight, x3 multiplied by a weight, and then you multiply. And what are these? They are the scalar value. You just multiply I1, I2, I3, I4, and you have got yi. And in this way, for all I equal to 1 to t, y1, y2, y3, and yt, you have got all of your y's. Each and every y you all can understand that this is a scalar value and this is a vector, so you will get a vector. So all of them are vectors, and if you add all of these vectors, you will get a weighted average of all the x1 to xt, and that is going to be a vector. That vector is actually y2. Is there any question till now? No. So your x is t cross k, that is okay to everyone. Your y is also t cross k, because all for each and every y x, you have got a y, and the dimensions of your x and y's are right now same, we are assuming. So this is also t cross k, this is also t cross k. What is the size of your w? W is going to be t cross t, because you are having, you wanted to learn that for when you, yes.
सर आपने ये जो लिखा है yi equals to wi1 x1 plus ये, तो x1 x2 तो sentences है ना?
x1 x2 सेंटेंस नहीं है, x1 x2 वर्ड है, ये उसकी एम्बेडिंग है.
ओके
ठीक है, x1 x2 वर्ड्स एंड दिस इज अ k डायमेंशनल एम्बेडिंग. Okay. Okay, fine. So x is t cross k, y is t cross k, and w is going to be t cross t. T cross t, because you have, only t cross t combinations which are going to happen, that when you are generating y2, then when you are generating y2, then you wanted to know that I wanted to give x1 to xt weights. So how many weights you are going to get? T weights you are going to get when you are generating y2. So for every y1, y2, y3, and y4, you, for every t, for y equal to 1 to yt, for every such thing you have got t things, and that's going to be a complete big matrix for you, which is being shown over here. W is going to be t cross t. And what is this? So by the way, this is that t weights that you have got. And if you wanted to generate, let us generate say y1. How you can generate? X1, x2, x3, xt. So what is going to happen is that you are going to multiply this, 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 and yeah, that is your y1. You add all of them, that is your y1. If you wanted to generate y2, then this got multiplied by this got multiplied by this got multiplied by this, and so on, and you add and you will get y2. One small thing that one should have to understand, that since it is going to be since it's going to be a weighted summation, these weighted summations need to be equal to 1. So if I add all of them, you are going to get 1. If I add all of them, you are going to get 1. If I add all of them, you are going to get 1. Is this okay? Is there anyone who want to ask any question? Then you can ask.
Sir.
Duplicate. Yes.
Yeah. Sir, so my question was, sir, so sometimes when you are translating languages, it can be possible that the input words are say 3 and the output words are 4.
Yeah, so that will happen. So right now I am only talking about self-attention. So in self-attention, the point is that it's going to learn an intermediate representations, which are not only going to learn things which are related to x2. It is actually learning that for y2, when you are making or predicting or generating, all the things which are related to x2, they are being used to generate this y2. Later we will use this to really generate sequence to sequence part.
Okay, sir.
So you will understand in some point of time.
Okay.
Yeah, but that's a valid question, and that was the thing actually I was trying to somehow address over here initially, but then I understood that right now it's not, wait for some time, then I will explain. So self-attention is the point which will take something and give you the same amount of things back.
Sir,
Yes.
sir, here x1, x2 is a k-dimensional vector, no?
Here your xi is
Yes, sir.
xi is a k-dimensional vector.
Okay.
Yeah. X is any xi is a word like I or wanted or to or something, and its word embedding is actually a k-dimensional word embedding, which is being shown over here. Yes, any other question? Yeah, because if you all understand, to generate y2, x1 got multiplied by this, x got multiplied by this, and to add all of them and you will get y2. So one thing is that since it's going to be weighted average, the values across the call rows, if I add, you need to get a 1. And how you can do this? Can anyone tell me that how I can do this? If I give you a matrix and I want that column rows, if I add, it has to be equal to 1. How can you do that? Anyone can tell?
So can I
Yes.
answer? So we can sum each row and then divide it by the sum.
Yes, that is one option. It can be done. That can be done, but usually we cannot do it in that way. In deep learning, what is the way in which we used to do? Let us ask it with Tanya, you tell me. No, Tanya, you don't tell. No. Rohit Bhamu, you tell me.
हेलो सर मैंने आज ही ज्वाइन किया 2-3 दिन से नेट सही नहीं था तो मेरे को
2-3 दिन से गायब थे। कोई बात नहीं। ओके। गीतांजलि, you tell me.
sigmoid activation function को use करके.
So if I do sigmoid, then sigmoid will take one value and convert it between 0 and 1. But here, if you convert, if you apply sigmoid over this or this or this, these sigmoids are going to give values or normalizing your weights between 0 and 1. But if I add all of them, how can they become equal to 1? What is the way by which we can do that?
Sir, using softmax.
Softmax, perfectly correct. Perfectly correct, yes. So you apply softmax, and softmax will take all of them and convert it into, addition is going to be equal to 1, and the value which is high will get more weightage, and the value which is less will get less weightage. The same thing we have done in the case of our previous RNN example, when we have learned weights for different H1, H2 and H3. It was 13, 9 and 9 probably, and over that you apply softmax so as to get the values between 0 and 1, and if you add all of them you are going to get 1. This is actually an exponential weighing. Yes, good. So one can say that xi, so forget this thing. Let us come over here. The weight vector. So this weight matrix I just have shown, W matrix, that is actually T by T matrix. And it's going to have Wij, any Wij, and all the values of i's are going to be 1 to T, and j is also going to be from 1 to T. And what you wanted to be, take it over here. What should have to be a value which is coming over here or here? What is the significance or the meaning between of this? So if I say that given any W, what is the meaning of Wi comma j? That is my question. What is the meaning of W of I comma j? Let us ask it again to someone. Arjun, you tell me. Arjun Sahdev.
Yes, sir.
Yes. So what is the meaning of Wij?
So that is the weight matrix. So मतलब y का क्या impact होगा x पे उसको find
Yes. हाँ नहीं तो which y and which x?
So जो 1 3 है, अगर 1 3 मतलब ij है तो jth x and ith y.
Yes. So it actually, you want to say the point is that xi and xj, if they are related, suppose that if they are related, then this value should have to be high, and if they are not related, then the value should not be high. Is this okay?
Yes, sir.
So can you tell me a way by which I can find out such a value?
NLL यूज करते हैं तो
क्या क्या करके?
नेगेटिव लॉग लाइक्लीहुड अगर रो पे यूज करें तो उससे आ जाना चाहिए.
नहीं, लेकिन पूरी रो से तुम्हें क्या लेना देना? अभी तो तुम्हारे पास रो वगैरह है नहीं. You only have got 2 vectors. If these vectors are related, this value should have to be high. Otherwise, this value should have to be low.
Yes, sir.
Then what is the way by which I can get such a value?
If
तो बहुत ही simple है ना. It's very simple thing. I have got 2 vectors. Are they related or not? How can you get that these vectors are related?
तो उसका वेक्टर का जो डिफरेंस है उससे देख सकते हैं. अगर कम होगा तो रिलेटेड होंगे, नहीं है तो रिलेटेड नहीं होंगे.
So vector का difference is going to be the Euclidean distance.
यूक्लिडियन L1 कह सकते हैं.
L1, L2. What is another way? Some other way?
Other than L1 and L2.
If I give you 2 vectors, how can you find out that they are going in the same direction?
So the ratio find करते हैं direction.
क्या ratio? Which ratio we used to find? Suppose that I am having a vector like this and a vector like this. This is V1 and this is V2. I wanted to find out the distance between.
Dot product.
Yes. Dot product, cosine similarity. That's called as cosine similarity.
Dot product.
Yes. So first thing is that that what we are going to do is this, and how to get this value. This value is going to be nothing but a function between this, and this function can actually be this dot product. Is this okay to everyone? It's a cosine similarity. And once you have got this cosine similarity, you have got the full matrix. In fact, if I give you x1 to xt, you have got this full matrix. In fact, W, which is a T cross T matrix. If I give you x1 to xt, Rohit, Bhamu, can you tell? Listen, Rohit.
Sir.
Yes. What I'm trying to say that if I give you x1 to xt, these are k-dimensional vectors. All of them are k-dimensional vectors.
Okay.
So if I give you such k-dimensional vectors, and how many t such k-dimensional vectors, then can you find out this W, which is actually a T cross T matrix, which has been defined, any ijth element is been defined like this. Can you find out?
Xi equal to Xi transpose Xj.
Yeah, you just have to take. So if you wanted to know what is W21, what it will be? Dot product between
X1 का transpose X2.
Yeah, whatever. So some transposition, but basically the x1 dot x2 That is the dot product you are going to get.
Yes.
This is clear?
Yes, sir.
So any ij you can compute, any wij you can compute,
Yes, sir.
and then any w, full w you can compute.
Yes, sir.
Given any input, if I give you t such inputs of k dimension each, this whole w is clear. No parameters are required. It's just the self-attention that is being realized using cosine similarity, and being, once you have got this complete full matrix of w, once you have got this full matrix of w, you can normalize it using softmax, row-wise normalization. Is this okay to everyone? Rohit, this is clear?
Yes, sir.
Okay, fine. Now let us understand what is happening inside once again. Very simple thing which is happening, and that is that I am getting, so I need to generate y2. I am going to generate some y2 using x1, x2, x3, x4 and all. So we all can understand that this is, you know, y4, and y4 is like India. So if you wanted to free India, then there is not only one religion who has worked for this. All of them have to be used. So Hindu, Muslim, Sikh and Isai, all of them are actually going to be used. X1, X2, X3 and X4, all of them are going to be used to generate this y2. But how we are generating? So let us see it one by one. That given x2, because we need to generate y2, so we need to find out that x2 is somehow related to the y2. We wanted to know that how many of you or others, they are having relationship with x2. So here you are checking x2 and its relation with x1, x2 and its relation with x2, x2 its relation with x3, and x2 and its relation with x4. And when you do that, you are going to get w21. And what was that? That's actually the relationship between 2 comma 1. That is the matrix we have shown over here, w1 or w2. So basically you are generating y2. How you can generate y2? x1 got multiplied by this, x2 got multiplied by this, x3 got multiplied by this. That is being shown over here, that x1. So here what is going to happen is that y2 is x2, x1 got multiplied by this, and whatever the value that you have got, that is going to be multiplied by x1. That is the contribution of x1 so as to generate y2. Now see that if this x1 is not related to x2, which means that its contribution is going to be very less. No matter how bold are you, no matter how important or how big value is this, if its weight is very less, then its contribution to generate this is also not going to be very high. Similarly, for the x2, you want to find out how much x2 and x2 are related, and then multiply this weight with x2 so as to get the y2. So you add all of them here, 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 and here. All the values are being added. So all these values are weighted using their relatedness with x2, and then they are added so as to get the y2. Is this clear to everyone?
सर if you're taking weight of x2 with x2, w22 तो हमेशा maximum होगा ना?
Yes, so it has to be the maximum because it's actually attention. So the attention of that you need to give to the current time steps need to be maximum. Is this anyways being obvious as well?
अच्छा ठीक.
Yes.
Sir, actually, this thing depends on the embeddings. Na? If suppose x2 has an embedding of say 1, 1, 1, it is a 4-dimensional vector, suppose, and it is
Yes.
1, 1, 1. So then it is possible that x2 will have a low value. I mean, weight w22 will have a low value. if
But it's
other
going to be soft
embeddings are
max, na?
something else.
Yeah, first thing is that these embeddings are also being normalized. Secondly, it's
Okay.
after normalization, these embeddings are also being soft maxed.
Okay.
So, yeah. So,
Okay.
so X2 is going to get the maximum. In fact, full weightage to X2.
Okay.
Suppose that all of them have got 1. If suppose that 4 things are there, all of them have got 1, then what is the weight that you are going to get? W21, 22, 23, 24?
0.25.
0.25. So you understand that if value is high, then all of them are high, or whatever the person, whatever the inputs who have got high value, softmax is going to work and suitably normalize the thing for you. That's okay. Now, there is some intuition which is being written that why self-attention works. I assume it is very, very simple, and which essentially mean that it's actually a movie recommendation example in which I'm having my movies, movie 1, movie 2, movie 3, and for every movie I'm having a vector that how much amount of romance, action and comedy is there, and similarly I'm having users. It's a 3-dimensional vector, and for every user I am also having a 3-dimensional vector which is saying that I like romance, how much amount of romance I like, or action I like, or comedy I like. And then if I give you a movie and a user, how can you find out that whether this user is going to like this movie or not? And the simple intuition is that the both of them are 2 vectors, and you just have to do this thing. Dot product is going to tell you that whether you are going to like that movie or not. So that was the intuition behind why such things are going to work. Now let us see, and all those things that word embedding need to learn in such a way so that related things are going to have more and more, related things are going to have very similar type of embedding, so that the dot product between them should be high. Now, all these things are fairly easy to understand. One thing that one should also have to understand is that when you are talking about sequence to sequence modeling, then if you have x1 to x5, 5 things, then they are being seen as input sets. They are being seen as input sets, and these input sets are going to be like high, and this means that the order is not going to matter. Do you understand this stuff? No? Am I audible?
Yes, sir, you're audible.
Okay. What I was trying to say is that I'm having a input x1, x2, x3, x4, and x5, and my sequence to sequence model is going to see it as a set, not as independent individual inputs. So, and what is the reason behind this? Because your network sequence to sequence will see this, and it is seeing them as a single set and going to produce a set of outputs. So if it is if it's actually a set, then x1, x2 and x3, they are same as x3, x2 or x1 or any permutation. Now is it clear that this is the way your self-attention module or sequence to sequence also, both of them are actually going to see it in this way? This is also called as permutation equivariance. Permutation equivariance. Because see, if you see it as a set and you are not producing anything, you are producing x1, x2, x3, x4 and x5, and then you produce y1, y2, y3, y4 and y5. So it doesn't matter that first you produce x1, then you produce x2, or first you produce x2 and then you produce x1. Because what is happening over here is that this multiplication is happening. And this multiplication doesn't change if this thing go here or this thing will come here. This multiplication remains to be the same. and the value that you are going to get addition, and y2 is remain to be the fix, whether you are having x2, x1, x3 or x4, or x4, x3, x2 or x1, whatever the permutation you show, you are going to get the same y2. Is it clear or not? Can anyone ask if you are not clear? I assume that was simple thing, and permutation equivariance is the point, and how to handle, because now you can argue. Pratik, you want to ask anything?
No, sir. You
Yeah, so now your question need to be that we understand that it is looking at this, and as I have explained that it doesn't matter, and the same thing is going to come if I show x2, then x4, and then x3, and then x2. So do you feel that this is correct? Because they need to be seen as the sequence, and if I change the sequence, why I am getting for all such permutations only one y2 is going to come. Do you feel that it is correct?
Yes, sir, because we are just adding them. I mean, we are just weighing and adding them. So no matter what the sequence is, the y2 will be same.
Correct. So this is happening in such in this network. But do you feel that such thing is good or correct when you are doing sequence to sequence modeling?
Sir, I guess yes, because say for a language translation task, x1, it is quite possible that x1 is not a dependent of y1 is not dependent on x1. It is dependent on say x4. So in that case, I guess.
Even that is also okay. But point is that if I show x1, x2, x3, x4, and if I change the sequence, then the language and its semantic is continuously changing. Suppose that I am having an RNN. If I show x1, x2, x3 and x4 and say that predict x5, it will predict something. And if I show x2, then x3, then x1, then x4 and say predict something, it is going to predict you something else, because words remains to be the same, but permutation is very, very important.
Yes, sir. But here we are not having that memory thing. Here we are just having weights, right?
Yes, but still you are only having weights, and in a sequence when you generate something, assume that now see that if I generate I am going, and then you say that am I going, and then you say going I am, all of them are going to generate same output,
Yes.
but they are generating same output because they are being weighted like this. But do you think that I am going, going I am, all of them are equivalent? All of these sentences are equivalent.
No.
Since these sentences are not equivalent, and since there is a strong sequence relationship or the positional relationship, or these permutations are going to play an important role while generating sequence to sequence modeling, it is being handled in a different way. And that is why I have written probably at some point that first you have to understand that they are being seen as set, so they are permutation equivariant, but this issue is need to be somehow handled in transformer, and I will show that how this issue is being handled. But you will have to understand that within transformer or within self attention, there is no ordering involved. You show any ordering and the same output is going to be generated. That's yes.
सर आप ऊपर जा सकते हैं क्या जहाँ पे वो डायग्राम है?
Yes.
सर इसमें सपोज अगर मैं इनपुट आई एम गोइंग देता हूँ तो एम जो है वो x2 है अपना. सो y2 के लिए जो अपन वेट्स जनरेट कर रहे हैं W21 W22, तो उसमें एम का कंट्रीब्यूशन सब जगह होगा?
नहीं होगा, सबका कंट्रीब्यूशन सबका सब जगह होगा, ये डिपेंड करता है कि होना चाहिए कि नहीं, वही यहाँ पे सिमिलैरिटी से निकल के आएगा।
हाँ तो वो इसमें x2 से ले रहे हैं ना अपन सिमिलैरिटी, m से लेंगे ना सबकी सिमिलैरिटी, i की
एम से
सिमिलैरिटी।
लेंगे, हाँ हाँ, अगर ये
But-
बनाने जा रहे हो।
हाँ बट जब अपन एम आई गोइंग करेंगे तो एम आई गोइंग
हाँ
में अपन आई के साथ लेंगे सबकी सिमिलैरिटी,
हाँ
तो सबके वेट्स अलग अलग हो जाएंगे। जब अपन आई सेकंड ले रहे हैं और एम सेकंड ले रहे हैं तो वेट्स अलग अलग आएंगे ना, तो फिर y2 सीम जनरेट कैसे होगा?
But the point that I wanted to make is that keep there these embeddings that you are going to get y1, y2, y3 and all of these yi's are going to be beta. All of these yi's are going to be permutation equivariant. Permutation equivariant means that if you come up with different type of permutation, then this permutation is not going to play that role. Permutation is only saying that okay, when I am going to generate this x2, then m I and going, then I am generating the same thing I, then I need to be taken, that is true, that I is
Okay.
going to be taken as this thing, and x1 and then x2, so here it's going to be m and I, so m and I, the same value is probably going to come because dot product is going to give you the same thing.
Yeah, correct.
Here it is going to be I and M. So I and M is again going to be the same. And
So this will be I and I, right?
sorry, this is going to be I and
Yeah.
I. And this is going to be M and M,
I-
M
I-
and
I and going. I and going.
M and going. Okay,
I
I
and going,
and
right?
going. I
Yeah.
and going. I and
Correct.
going. Yes.
Yes.
So the same thing is going to happen. The only point that I wanted to make is that the permutation information is not tightly embedded in transformer or self-attention networks, because the point is that if I show it in a different way, what is going to happen is that probably, as you have said, that x2s they are changing, that is also correct, but the semantic is not intact. I am and going, this semantic is so what is the position of a word is only coming from maybe this embedding.
Yeah.
Only coming, yeah, maybe only coming from by this embedding, and it is not very tightly coupled with the network. This has to be
correct.
somehow understood by the network itself, that okay, if I need to generate y2, then I have to give more weightage to this, and why? Because this value anyways is going to be high, whatever you are showing. But this is only the embedding which is telling that how much, what is its position. Explicitly, there is no position involved, position information involved, other than if I say this. And that
Okay.
is only for which one? That is only for this guy, to which you are going to generate. Others, they are not very much, coupled with their positions are coupled with their embeddings, because these embeddings are actually being computed irrespective of their locations, because word embeddings are irrespective of their location. Now in RNN, what happened? That you have got, x1, then you show x2, then you show x3. This is unrolling. And that is tightly coupled, that you all can understand that first I need to show x1, then I need to show x2, then I have shown x3. And this is the context that you have got. What is this context? This context is that when I see x1, then x2, then x3. If I show x3, then x2, then x1, then the context will change and drastically change. So because of which these embeddings are, although they are not having any positional information, but they are being shown at a very specific amount of time, and that is why it was sequential. And because of that, it doesn't require or not having this positional equivariance. But positional equivariance is also not required, because if I change the position of sentences, words got changed in a sentence, then it's completely different semantic. They are started to carry a completely different semantic. So because of that, what's going to happen is that transformers need to somehow as opposite to RNN, transformers have to explicitly see that what is the location. Along with the word embedding, we have to tell that what is the position of this word. That is also important, and that we will see in some point of time. I'm sorry, I've taken good amount of time up to this. So after this, in next lecture, I'm going to cover. Till now, if you have any question, then you can ask.
Sir,
Yes.
just to clarify,
Yes.
once can you go to that diagram?
Yes, here.
Right. So about permutation equivalence. So what I understand is, say I have x1, x2, x3, x4, and
Yes.
it has its corresponding y1, y2, y3, y4. Say I am going, so
Yes.
I is x1, so that I is giving some y1.
Yes.
Now when I change am I going, suppose, so x1 becomes am. So then
Yeah.
there will be y2 in place of y1. So that is permutational equivalence, right?
Yeah, that is there. But at last, when you get y1, y2, y3, y4, then what is the correct ordering? You do not know that what is the correct ordering.
Right. So these are basically corresponding things. X1 will always correspond to Y1. X2 will always correspond to Y2. If you change the order, if you put X2, X1, X3, X4, then there'll be Y2, Y1, Y3, Y4, right? Like that.
Yeah. So if I show it in the wrong order, then there is a corresponding output.
Wrong order output.
Yeah, wrong order output. So how you can figure it out that what is the correct ordering out of that? Maybe it is doing the correct work.
Right.
One-to-one correspondence is there. So maybe it's trying to give you the proper output, but what is the correct ordering is going to be missed. So along with the word, if I give you the correct ordering as well, then output is also going to be in the correct order itself. So that we will talk about and tell you about this positional embedding, maybe in the next lecture.
Okay. So this is a problem which the transformer can overcome.
Yeah. So the problem is this, and RNN was not having this problem. That is the issue. RNN specifically understand that at t equal to t, I need to see this.
Right.
And that is why it was sequential. And that is why now you can see that this is the single matrix multiplication, and it is very, very fast because it can be parallelized.
Right.
So there you cannot see x1 to x4 in one time instance. You have to wait for, first see x1, then x2, then x3, then x4. Here you can see all of them at the same point of time and generate y2 directly. So that is why it is fast. But the problem is that timing information is actually being left. We have not even any place talked about that what is the timing information of x1 or x2 or x3 or x4. They're not being used at all. In RNN, they were also not being used, but they are being embedded in the network of RNN itself, because it will see a word at a specific time. So transformer need to address this. Otherwise, it will be completely positional equivariant. Okay. Yes. We are done for today. If you have any question, then you can ask.
Sir, can you name the blog again?
Yes. You can write it down. Peter Bloem. Anyways, you write transformer, then first blog. He has written a very, very good blog. peterbloem.nl/blog/transformers. You will get it. Okay. Thank you.
Thank you, sir.